In this video, we're going to carry on our discussion of the effects of the sympathetic nervous system and really start to focus in on the target cells. So when we're looking at the sympathetic nervous system, in the previous video, we had walked our way through some of the effects on things like smooth muscles. Now let's talk a bit about the effects on cellular metabolism, because this is really how hormones and neurotransmitters, especially in the autonomic nervous system when they're going to a target organ, this is how they really dictate what the effect will be. It's basically about turning on, turning off, or modifying cellular metabolism. So not surprisingly, during sympathetic activity, and of course sympathetic activity, and we always think of the fight or flight type phenomenon, many cells will require a higher amount of ATP because we're going to put greater demands on them in terms of their metabolism. So nearly all cells, and especially things like skeletal muscle cells, will require high amounts of ATP. So it's not surprising that one of the effects of the sympathetic nervous system is to basically provide these resources to the cells. So let's have a quick look. So we have the beta-3 receptors that we find on fat cells, adipocytes. And what they do is, when they're triggered, they result in the breakdown of lipids. And that helps to release free fatty acids into the bloodstream, which then can act as basically a fuel source. We also have the action of beta-2 receptors on liver cells, and they trigger the release of glucose from the stored glycogen. Remember, glycogen is a big storage molecule made up of a number of monomers of glucose. So we can start to break down that chain of glycogen and start to release glucose. The other thing that can happen is we can make glucose from other sources, like gluconeogenesis type of phenomenon. Also binds to the beta-2 receptors on cells of the pancreas. And this triggers the release of the hormone glucagon. And of course, one of the main functions of glucagon is to increase blood glucose level. So you can see that through a number of mechanisms, by changing cellular metabolism, I can have a situation where there's sympathetic activity, I need more ATP, and there's a number of ways that we can basically generate those resources that will help you do that. Now, how about some other tissues? So how about the effects of the secretion on sweat glands? So not surprisingly, sympathetic nervous system activity will try to maintain body temperatures during periods of physical activity. So of course, when muscles are contracting, one of the byproducts is heat. So we have to really think about how do we dissipate some of this heat. So the postganglionic sympathetic neurons release ACH at the target of the sweat glands in the skin. And the ACH binds onto the muscarinic receptors. Remember, there's different categories of receptors. So muscarinic receptors. And this will increase sweat gland secretion and therefore help to lower the body temperature. Now, your book does a really good job of having summaries, and here we're looking at the main effects of the sympathetic nervous system on target cells. So this is a really good visual to help us try to understand what's happening. And I would say this is a really great place to spend a lot of your time when it comes to review and really trying to understand what is happening. Now, let's talk about the adrenal medulla. Now, we haven't talked about the adrenal glands before, but the adrenal glands are interesting. They're actually two glands in one. We have actual glandular tissue, and embedded in that we have what is basically a modified ganglia that we'll have a look at in a second. So the adrenal medulla sits on top of each kidney, and it's in direct contact with the preganglionic sympathetic neurons. And as I said, the medulla is composed of modified sympathetic post-ganglionic neurons. And let's have a look at sort of what is happening here. So, ACH is released from the preganglionic neuron, and that follows the general game plan that we've seen before. And here it binds onto nicotinic receptors on the adrenal medulla cells. And the ACH stimulates the medullary cells to release norepinephrine and epinephrine into the bloodstream. So as soon as those, let's stop for a second, because we're going, what? Those are neurotransmitters. Well, here's something to remember, is that many neurotransmitters can actually act as hormones if they're released into the bloodstream. And when we get into endocrinology, we'll see this is the case. The other thing to know about the adrenal medulla, this is one of those places in the body where the nervous system and the endocrine system are kind of fused together. This is where they meet. This is their interface between the endocrine and the sympathetic nervous system. So, in this case, we end up with a release of norepinephrine and epinephrine into the bloodstream, and they act as hormones. And of course, once you enter the bloodstream, you can travel all over the body. So, you act as long-distance chemical messengers. And here we can see this concept that the preganglionic neuron, travels, and in this case it's synapsing with what is effectively the postganglionic tissue. But in this case, the ACH binds to nicotinic receptors in the adrenal medulla cells. And in many ways, the adrenal medulla, as I said previously, is basically a modified postganglionic neurons. And as a result of that, norepinephrine and epinephrine are then released, and because of the vascularization, things like that, big capillary beds, these chemicals are picked up by the bloodstream, and they then functionally become hormones. So it's a really unique situation where the nervous system and the endocrine system meet and work together. Now, how about some other effects on other cells? Well, there's a number of other target cells. But really, what's the main thing we're trying to accomplish with all the other cells? It's about maintaining homeostasis during increased physical or emotional stress. And these are about trying to do things like enhance your mental alertness. So not surprisingly, one of the side effects is that we get increased neuronal activity in many parts of the cerebral cortex that have to do with mental alertness. And also what happens is we can get a temporary increase in the tension, the force, generated by skeletal muscles during muscle contraction. And maybe this is what's behind, you hear those stories about people under emergency situations. They get these, this short-term temporary ability to outperform in terms of muscle performance because of the adrenaline epinephrine rush. Now, some of the other things that can happen is, just as sort of to add to our list, is that we have increased blood tendency to clot. Now, why would that be? Well, think about it. If you're involved in fight or flight, you're more likely to be injured. If you're more likely to be injured, you may be more likely to be bleeding, therefore making your clotting system a little bit more effective temporarily may be a benefit. The other thing is that the post-ganglionic sympathetic neurons trigger the contraction of these little muscles associated with your hair on your body. And these are called the erector pillae muscles. And these are the ones that produce goosebumps. So yes, sympathetic activity can lead to goosebumps. And also, it can have an effect, it can cause ejaculation of semen because it affects smooth muscle cells in the male reproductive ducts, and this helps to propel the ejaculate. Now, we're going to ease out there, and the next one we're going to come back and we're going to carry on talking about neurotransmitters and receptors and go on to some more information.